Hello everyone and welcome back. So let's do a more involved problem this time. And so what we're going to have this time is actually a reflected... Ooh, I'm going to use blue for this. Let's get rid of that. What am I doing here? I want to use black. There we go. So here's a wall down here. Here's a wall, and I have a turning angle of some sort. That'll be an angle theta. Okay. And so let's make that a wall. Beautiful. Beautiful. Perfect. And that's a wall too, just so you know it's going uphill. Now this is going to cause a shock. The shock's going to go up to the ceiling, it's going to bounce off, and it's going to be reflected. We haven't talked too much about this, and so we're going to be learning as we go. Nice, right? And then here's my streamline coming through this. It turns up, and then it turns again. Because it has to, because there's a wall there. It can't run into the wall. We don't let things run into the wall. And this right here would be that turning angle there. This right here would be that turning angle. Let's see here. Anything else here? I can go ahead and mark that off. That's going to be beta 1. That would also be beta 1 just from geometry. And we can start labeling some other things. I'll have M1. I'll be going up after that because it's got to turn with the floor. And I'm going to have to turn once again when I get over here. M3. Okay, that looks pretty good. That looks pretty good. Now, what does it give us? Well, first off, it gives us that this guy is equal to 18.2 degrees. Second, that M1 is going to be equal to 3.2. My pressure 1 is going to be equal to 3 atmospheres. And my temperature 1, we're getting a little bit of room there, some over here, is equal to 570 Rankine. And what we're going to try to find is going all the way over here. What is M3, P3, and T3? After going through 2 shocks, man. We also want to figure out what the angle the shock makes with the upper wall. So what is this angle right here, which we're going to use that symbol for? Beautiful. Okay, now we're going to need our normal shock properties tables. We're going to need that diagram, that theta beta Mach diagram. And we've got a lot of stuff to do here, so let's get right to it. Let's scroll this up a bit. Now, for this one, we're going to deal with this first shock wave just like we've dealt with all of our other oblique shock waves. If we're going to do it, we've got to first figure out what is my original my normal Mach number to that shock wave. And so our normal Mach number to that shock wave equation is M normal comma 1 is equal to M1 sine of beta 1. But we don't know what beta 1 is. And just to continue to try to like drill it into your head how to use those diagrams, we're now going to go with magic, the power of moving magic, to that theta beta Mach diagram, and we're going to see what it would be for a deflection angle of 18.2 and a Mach number of 3.2. Ready? So here we go. And we've been transported here. Now, if you wonder where this is, you can find it on the internet, obviously, but I'm going to the oblique shock relation section of our textbook. That's where I'm going to find it. And that's section 9.2 in the 7th edition. I go all the way down here, and I get to this guy. Now this is a absolutely terrifying, absolutely horrible diagram. Not because it's a bad diagram, simply because it's a lot to look at, okay? It's a lot to look at. So let's go ahead and figure this out. Now I'm going to do my best here. I'm going to go ahead and start screenshotting this, capture the full page, just so I can zoom in a little bit here. Okay. So first things first, is it going to be a weak or a strong shock? It's going to be a weak. I'm just getting that based on geometry. It does not, I'm not expecting it to be a strong shock. If I had higher pressure ratios, maybe it would be, but for this one, it's pretty low. Let's just assume it's a lower one. So right here, this line, that is 3.2. And so I'm going to just go ahead and make it easy for myself, and I'm going to color that guy red. What am I doing? I've got a pen. Let's make it easy myself. There we go. If you don't have a pen, maybe get like a projector slide kind of thing, and you can use that to help yourself out. Trace it. Or you can just plug it into the equation. There is an equation for this one. It's just not the best thing in the world. Okay, now I need to find my deflection angle, which was given to us as 18.2 degrees. So let's see right here. So this right here is 18. So 19 is, let me make sure I do that right. Yes, that would be 19. So I'll be just to the right of this line right here. So I'm going to go up here and say that I'm just right about there. And if I go over, I would hit somewhere around here. So that is 34. Okay, so beta should be 34. Yep, 34 degrees. Okay. Now your book actually says it's 34.2 degrees because, you know, they have magical powers, and also because they're not using a diagram, they are actually probably plugging into the equation. Now I'm going to go ahead and jump back now that I've shown this to you, and I'll see you on the problem in just a second. And we're back. So I'm going to plug this into my equation now, remembering that we got from the diagram that beta 1 is equal to 34.2 degrees. If you'd done 34, you would have still gotten this problem correct. Like, you don't have to be that exact. If you're using the equation, you can get it much more close, but that equation is terrible. I don't like using the equation. We got a diagram, you use the diagram. So let's plug this in, 3.2 sine of 34.2. And that comes out to be equal to 1.8. Okay, so I've got that first normal Mach number. Good. Now, where do we go? Well, we have a normal Mach number, which means we're looking at this no longer as an oblique shock, so we're going to go to the normal shock tables. Which in this particular textbook is Appendix B. So let's go ahead and jump over there right now. So I was over here, I'm going to exile that. And we're going to go down to Appendix B. Let's see here, there we go. Okay, so things we're really going to find is, one, what is our normal Mach number after the shock? What's M2? And also, you know, what's my ratio of pressures, what's my ratio of temperatures, because I want to find my pressure and temperature at the end, and that's how I'm going to do it. So I'm going to scroll up here. I have a Mach number of 1.8. So be very careful because this is times 10 to the first. So I actually need to find 0.18 on this diagram. I found it. And now I'm going to go ahead and screenshot so I can underline all the information so you can see it a little bit more easy. So right here, this is the line I care about right there. And I want the pressure ratio, which is this column right here. If you're wondering, how do I easily know that? Well, I've looked at the diagrams quite a few times now. I'm getting better at doing it. Also, I can just look at the headings at the top if I need to remember. And this one right here is the temperature ratio. So this is P2 over P1. This is T2 over T1. And this guy way over here, that is going to be MN2. Because remember, if we have an oblique shock, all we're finding from these tables is what our normal Mach number is, not our total Mach number, not our actual Mach number. Okay, now that we have that information, we're good to go now. So let's keep on going. Let's jump back to the problem and start solving some more of it. So I now know that MN2 is equal to 0.6165 P2 over P1, that doesn't look like much like a P, there we go, is equal to 3.613, and T2 over T1 is equal to 1.532. Okay, so that's going pretty good. Now let's find out what our actual Mach number is behind this shock wave. So M2 is going to be equal to my normal Mach number 2 over sine of beta minus theta. This will be beta 1 minus theta 1. Because that's what's causing this shock wave in the first place. And so I plug it in, I get 0.6165 over sine of 34.2 minus 18.2. Which obviously, me doing this in my head, would become 2.24. Okay, I didn't actually do it in my head. I lied to you. I just looked it up in the solution. It's easier for me to get the numbers from that. I am showing you where they all come from. Don't forget that, okay? Don't forget that. Okay. So let's get back up to our picture here and realize that we're now about to hit this reflected shock here. We're about to hit this reflected shock. And so we're going to have to figure out some information about that reflected shock. So the big thing to remember here is my angle theta. I'm going to go ahead and circle this in a different color. Right here. So my flow has to turn. It has to turn such that it is going to be parallel to that upper wall. It always has to do that. And so my shock wave has to help it to do that. And so that's actually how we figure out what theta is going to be. So we look at it, theta for that angle that the shock wave is taking is going to be equal to my original deflection angle. Reason for that is because I have deflected it 18.2 degrees upward, and now I have to deflect it 18.2 degrees downward. So that is what's going on there. That is why I'm having to do that. And oh, sorry, I'm looking at the wrong angle. My bad. Okay. The deflection angle is theta. Sorry, not the wave angle. My bad, my bad. Okay. Your teacher can make mistakes too. Here, let me do this a little bit. There you go. Sorry. The deflection angle is 18.2 degrees downward, not the wave angle. Not the wave angle. That's wave angle is what we're trying to find out. And we're about to get it. We're about to get it. There we go. Finally got my... Sorry. This angle right here, that is my deflection angle. That is equal to theta because that angle is theta. This one we have to find out from our diagram. Sorry. Make your teacher go on. Teacher goes on crazy tangents sometimes. So clarifying once again, I deflected it 18.2 degrees up, and so I didn't have to deflect it 18.2 degrees downward to make it parallel once more. Otherwise, the flow would not be parallel. And so using that information, I'm going to go to my diagrams. I'm going to go to my theta beta Mach diagram. I have a Mach number of 2.24. I have theta, which is equal to 18.2 degrees. And then from that, I can find out what my beta is going to be equal to. Like, wouldn't it be the same because you have the same deflection angle? Remember, we had a different Mach number. So let's jump back now and go to our theta beta Mach diagram and see what it'll be for a Mach number of 2.24 and a deflection angle of 18.2 degrees. Okay, so here we are at my theta beta Mach diagram. As a note, I've already taken the liberty of helping this out and screenshotting it. So I'm going to go down here. So just so we can see, oh, well, I'll have to trace this line first. So first thing I'm going to do is I'm going to go ahead and trace 2.2 for my Mach number. Technically it's 2.24, so it should be a little bit in front of this line right here. I'm just going to go ahead and trace the 2.2 line because that's going to make it easier on me just to place myself. And then I'm going to remember that I'm slightly in front of that when I'm doing my calculations. Okay, so I've got that line traced. Now I've got to go down to 18.2 degrees. So 18.2 is slightly in front of this line, so I'm going to go ahead and go up. Doing my best to trace it. Oh my goodness, that is not a straight line at all, but I'm doing my best. Okay, so if I'm slightly in front of this guy and slightly to the right, I'm somewhere like around here, I feel like. So I'm going to go ahead and choose that point, and then I'm going to go over right around there. And I hit somewhere around, let's see here. I always say it's almost 45. I'm just going to say 45 degrees, okay? We're just going to say 45 degrees. That looks good to me. Yeah, that looks good to me. So we're going to say that's 45 degrees. Okay. Just letting you know, it's actually 44.95, but come on, like that was so close right there. How would you know 44.95 looking at this diagram? Okay. So what we got from the diagram is that this is 45 degrees. Boom, nice, looks good, loving it. Okay. And so with a 45 degree angle, we have all that information. That looks good. Let's go ahead and find our normal shock properties for that shock wave. Yeah, why not? So first off, M normal 2, okay? This is, as a note, this is going to be different than earlier. Actually, will it be different? Yes, it will be different. Okay, M normal 2, just so you don't get confused, calculating M normal 2 here and M normal 2 here are very different things. And this is going to be equal to, let's see here, M2 sine of beta 2. Okay, we have beta 2 now. We got that good stuff. We plug this in, I get 2.24 sine of 45 degrees. And that's going to be equal to 1.582. Yeah. Okay, now we've got a normal Mach number. We go to the normal shock tables. So let's go to the normal shock tables again. And appendix what? It's appendix B. Okay, here we go. Okay, now we're in the normal shock property tables again. Now I've got a normal Mach number of 1.582, so I need to find 1.58. Am I going to interpolate? No, I'm not. Will it be slightly off because of that? Yes, slightly. And that is completely fine. That is completely fine. So let's go ahead and see what these values are. Now, to help myself out here, I'm going to go ahead and capture my screen so I can underline these. Let's see, screenshot, capture full page. And let's go across. So 1.58 is right here. And so this is my pressure ratio, and this is my temperature ratio. So this would be P3 over P2. This would be T3 over T2. And going all the way across, this would be MN3. Okay, I should have everything I need there, so long as I'm on the right line. And I am. So it looks good there, looks good. Feeling good about it. Okay, so let's go ahead and take those values over and write them in our problem statement. So we have that P3 over P2 is equal to 2.746, I believe. Yep, and T3 over T2 is 1.374. Beautiful. And our MN3 is going to be equal to, what are you? 0.6746. Okay, 0.6746. There we go. We got our information from the normal shock tables. That's all going to be helpful. And by having this and this, we can already calculate what our temperature will be at the end, as well as what our pressure will be at the end. So we're doing really good here. We only have a little bit more to go. So let's go ahead and calculate our Mach number, and then we'll calculate our pressure and temperature. The final thing we'll do is we'll calculate that wave angle. Okay, we'll calculate that wave angle. So let's see here. So first off, M3 is going to be equal to my normal Mach number 3 over sine of beta minus theta. Yep, beta minus theta. There we go. Looks good. And that's going to be equal to 0.6746 all over sine of 45 minus 18.2. And let me see what that plugs into when I play with my calculator. If you wonder why I'm suddenly having to play with my calculator, is because, yes, I do actually look at the solutions to help me go through these problems more quickly. And so I can pull the numbers without having to constantly do it in a calculator. But the solution in this problem actually made a mistake. And so I have to do my own now. There we go. Okay. I get that its Mach number is 1.496. So just if you're wondering, I do actually try my best to check these problems as I do them. I can't say I always catch the errors, but I do most of the time. How do I know if I don't catch the error? Probably because you would tell me. There we go. So I always catch the errors because I am perfect without flaws. Okay, let's find P3 and T3 now. So P3 is going to be equal to P3 over P2 times P2 over P1 times P1. Hopefully you're getting used to this kind of stair-stepping kind of thing. So that's going to be equal to 2.746 times 3.613 times 3. Okay, and I'm just going to get the calculations both at the same time. I'll write everything out first. So T3 over T2 times T2 over T1 times T1. That's going to be equal to 1.374 times 1.532 times 570 Rankine. Okay, now let's plug both those in a calculator and see what we get here. See what we get. I'm guessing 11. As a note, that's just me being completely random. I don't have any idea what that number's going to be. Okay, it was not 11. Sorry, everybody. The pressure is 29.8 atmospheres, because it was atmospheres originally. Okay, we got that one. And now let's figure what our temperature would be. And it would be equal to 1,200 Rankine. Woo, warm. Warm indeed. Okay, so we got it. Now the last thing we have to do is to calculate this angle right here. What is this angle? Now I'm going to redraw this at the bottom so that I can teach you something else that would be very, very helpful to you, because we've been doing something this entire time. You never even realized it, and you didn't even know what we were doing here. Okay, so let me go ahead and try my best to redraw that. So it reflects, and we had, something like this, and then we saw that it was going to be, that's our streamline right here. This is our deflection right here. Perfect. And we're trying to figure out, make sure I'm doing this right, what this angle right here is. We call that this. That looks right to me. Make sure I'm going to go back up here and check one more time. Just make sure I drew it all perfectly. I did draw it that way. Happy days, happy days. It looks good. Okay. Now, this angle is not equal to beta. It's not, I'm sorry. How do I know that? Well, I actually know it from an equation we've been using an awful lot. I've never really taken the time to explain. It's this one right here. So M3 is equal to M normal 3 over sine of beta minus theta. So this is how we get our regular Mach number, by knowing what our normal Mach number is. And so if I'm really going to draw it on this diagram over here, my normal Mach number, or my regular Mach number, is right here. This is M3. And I have some normal component of that Mach number that goes like this. That right there is M in. I did a terrible job. It should have gone along that line right there. Okay, let's try my best here. Yeah, this is what I'm going to do. And so I have a normal component right here. That's going to be M in 3. And then I have some other component which I don't care about. Okay. So angles. Angles are important here. Now, if I'm looking at this diagram right here, that theta gets in the way, so I'm going to remove that theta. I'm trying to figure out, well, what is M3? And I'm using sine right here. I'm using sine. So we have our right angle right here. There we go, right angle. Now let's just draw this, blow it up again, because I'm going to have trouble with all this if I don't draw it up big. There we go. So M in 3, M3. Perfect. And so I'm using sine, which means I'm using this angle right here to solve for M3. And if we look at this, what we're getting is that this angle is beta minus theta. And so I'm using, okay, M3 sine of beta minus theta is equal to M normal 3, or I divide both sides by sine beta minus theta to get it. Now you might have thought it was strange, like, well, why is that angle beta minus theta? Well, it is because our deflection angle does not actually go normal. It's somewhere like right here. And so I'm like, okay, well, this one right here, that angle is theta. This angle right here is beta minus theta. And I have some other like mysterious angle right here, which we can talk about later. But what I'm going to tell you right now is that this angle beta minus theta, that is our angle that we're actually looking for. Okay, that is the angle that we're looking for. The angle that the wave makes with the wall is going to be beta minus theta in this case. And I needed to know that because I need to be able to tell what angle the wave is making with the wall, so I can tell exactly what my normal Mach number is going to be. Sorry, my Mach number will be from that. Because that angle has to be set properly such that the flow will turn the right amount. It has to turn that correct amount. If it doesn't turn the correct amount, everything goes horribly, horribly wrong. There's a little jump there. I just wanted to go see something first. Okay, now let me show you one last thing. Go up here. We have this weird angle once before. So this angle right here. Oops, sorry, wrong one. My bad. I just hit the undo button. Why am I not hitting the undo button? This angle right here. Okay, that is the angle that the wave makes with the floor. The oblique shock wave makes with the floor. And guess what? That angle is also beta minus theta, which is equal to the original guy. So just know that's where it's coming from. We're always getting beta minus theta. That is that angle we're needing because we need to know, because we always know that our Mach number is parallel to the floor. And so when I'm trying to find my Mach number from my normal Mach number, I have to know the angle that makes me parallel to the floor. Okay, I have to make the angle that helps me get parallel to the floor again. So that's what it's trying to do there. It's always I always use that angle that is telling me how much the oblique shock is from the floor, because the floor is my reference. That's what the normal Mach number is going to be parallel to. And so that's why it's always that. Okay, so with that in mind, we know that this is not equal to beta. It is equal to beta minus theta. Okay? And so since it's beta minus theta, that means that it is equal to 45 degrees minus 18.2. And what is that when I plug it in my calculator? 45 minus 18.2 comes out to be 26.8 degrees. There you go. So we solved the problem. We found our temperature, we found our pressure, we found our Mach number, and we found the angle with the wall. Just remember, big important details. This angle from the wall is set such that you can make your Mach number parallel to the floor. And the way you find that angle, that it's been deflected, bounced off the wall, is going to be equal to beta minus theta. So you can know theta because that's deflection angle. The second one, beta, you have to figure that one out by looking it up in the tables to see, your theta beta Mach tables, to see how the flow would be turned based on your original Mach number and the deflection angle. So, thank you all so much. I'll see you all next time. Bye-bye.